My name is Fernanda Leomil, and I'm a PhD student in biophysics at the Federal University of São Paulo in Brazil, and now a visiting PhD student at the Max Planck Institute for Colloids and Interfaces in Germany. During this presentation, I will introduce you to POET, a software for pore agitation calculation in GUVs. Electroporation, that consists in the opening of transient pores in the membrane in response to a high-intensity electric field, has emerged as a very effective technique to introduce directly into cell cytosol different types of molecules. Given the extent of its applicability, it's very important to understand the stability of biological membranes in response to electroporation. A typical strategy for the study of physiological phenomena involving cell membranes is the usage of model membranes. They are composed of a minimal set of components and allow the control of the composition and many other parameters. In particular, giant unilamellar vesicles mimic the plasma membrane size and curvature and can be easily observed and manipulated under an optical microscope. Okay, given that pretty useful model membrane, how could one characterize membrane stability after electroporation? One way of doing that is through the characterization of a widely known membrane material property called pore edge tension. This property is intrinsic of the bilayer composition and reflects the energy cost of maintaining an opened pore in this membrane. Based on the theoretical work of Brochard-Wyatt, Portet and Dimova proposed a method to calculate pore edge tension on a GUV subjected to a DC electric field. In this method, one has to first create a pore in the membrane. After that, one has to measure the pore closure rate, tracking pore size frame by frame, which can then be related to the pore edge tension according to this equation. It's possible to track pore size manually with an image processing software. However, it has proven to be time-consuming since these videos can contain hundreds of frames and also inaccurate since manual measurements on digital images may be quite inconsistent. POET is an open-source software for automatically and precisely calculating pore edge tension. It was developed in Python, and it works with TIFF image sequences obtained from experiments with phase contrast microscopy and analyzes a pore facing the bottom of the image. It performs important image processing steps that are normally necessary for this type of analysis, and then crops the image in half its height to focus the analysis only in the bottom part. The pore size measurement step consists in labeling connected elements in each frame and verifying how many elements are there. If only one element can be found, that indicates that the pore is closed. But if two elements can be found, then this suggests that a pore was opened. In the latter case, to measure pore size, the two elements are first identified as being the left or right elements, based on the x-coordinate of their centroids. Then each element extremity is found and the distance between these edges is calculated and computed as the pore diameter. POET also measures the UV diameter and, together with pore radius, plots the pore dynamics graphic where the user is prompted to manually select the linear region. Then it performs linear regression on the selected interval and calculates pore edge tension by resolving the angular coefficient in the equation previously shown. POET has a very intuitive graphical user interface. Its efficiency was evaluated by comparing manual and automatic analysis performed on the same sequences. The results were similar, and the employment of POET reduced analysis time in 96%. We also validated and demonstrated the suitability of POET by comparing the pore edge tension for neutral GUVs containing different fractions of charged lipids of non-biological relevance, such as phosphatidylserine, cardiolipin, phosphatidyl'inositol, and phosphatidyl'inositol bisphosphate. A twofold reduction in pore edge tension was verified only for GUVs containing 50 mol% of anionic lipid. Thanks for listening to my talk. And to sum up the most important points,
POET is able to show how a pore in a membrane could quickly grow. We use POET as a tool to show that biophysics is cool.